Okay, so I hope all of you had a nice, relaxing Thanksgiving. These are just the topics for this week. Hopefully, we get through at least this first part, and then there'll be some Fresnel diffraction, which I'll probably some of it I'll post as videos for some of the math, and for some of this I'll follow up with the physics part mainly in the class. Okay, so let's get started today. Before I get started, hopefully you all noticed that your test 2 scores are now posted on Gradescope and Canvas. The solutions to the test 2 part 2 are posted in Canvas, so that should hopefully explain your grade to you. But if you still have questions about how it was graded relative to the solutions or relative to anything, any other concerns you have on that test 2 part 2, then please contact me immediately. The plan is to have a final test during finals week following the same format, basically a take-home exam for like 48 hours, and which will mostly cover, I think, the part after the test 2 part 2, which is diffraction. This is what we've mostly focused on the last few weeks, but it will also have some questions from earlier parts of the course. I'll announce the further details by the end of the next week, so you know how to prepare for the.
So what is the time period during the final week for exam? Well,
it will be similar. 2 days basically. 2 days take home.
What's the specific two? So what are those 2 days? Like Monday, Tuesday, or?
Oh, do you care so much? It's all take home anyway. Does that matter? I mean, if it matters, I can pick. I was thinking like something like Wednesday, Thursday, because Wednesday is the day of our class, the first day of our class. So probably Wednesday, Thursday, I might post it like Tuesday afternoon or something, and then you have basically till Thursday evening or something like that to finish it.
Yeah.
If that's reasonable for everyone, if anyone has any specific concerns with travel or something, I mean, you shouldn't be traveling. That is finals week, so you shouldn't have booked any travel that week. But I'm willing to try and work with you if needed. But you must approach me with that earlier, ahead of time. Don't tell me that after the test has been posted. Okay. I did want to cover one thing, which is I noticed that test 2 part 1 for some. Let me see. Can I show that? Okay. Yeah. It's there. Which was that is when I looked at the part 1, I noticed that question 1 and 3 in the test, which I mean you may have different numbers when you took the test because it shuffles those questions, but I'll just go over the questions so hopefully you recognize them. I noticed these 2 were the ones that seem to give people more trouble. The others most people got right. So let me bring up those 2 questions. Okay, so question 1, which you should have seen, is this one. Electric field vector of a particular electromagnetic wave is given by cosine, E naught x, E naught y, x hat, and then y hat. So that's just the x and y components, and each of the x and y components has an amplitude, E0x, and then of course the phase, right? Cosine of some phase, plus similarly E0y, the amplitude along the y direction, cosine of some phase, where here the phase has an extra plus pi over 2 added to it for the y component. And as you may remember, then when we have positive epsilon, then that component is going to lead or lag behind the first. Anyone remember? Because of the minus sign, it's going to lag, right? So therefore, that is when there's a minus sign, it leads for the phase, or another way to think about it is just this: there's a minus sign in front of t, so therefore that's going to lag behind. Anyway, if you didn't get that right, I mean, in the end, that ends up being left circular forwards. Okay, all right. The other one was any questions? if you're not sure, yeah, you can come talk to me, or again, we can go over it and after the class. The other problem was, this is from your lab, and this surprisingly seemed to give people a lot of problem. Again, because you did this in the lab, which is that there's that setup. I even referred you to the part 2 because I reproduced the setup for the lab in that part 2. But you can also refer to the figure in your lab manual, of course. And you set up this reflected beam from the prism, the glass prism. The incident laser is polarized at 45 degrees to the vertical, and the incident angle is given to you set to be at Brewster's angle, which is 56 degrees for this particular glass prism. So for the polarizer that's in the path of the reflected beam, when will the transmitted intensity be maximum for depending on the rotation of the transmission axis? Well, we know at Brewster's angle, the polarization of the beam, which is reflected, will be along the S-polarized, right? It will be purely S-polarized because P-polarized is not reflected. P-polarized is 100% transmitted at that angle. And therefore, the reflected beam coming back will be purely S-polarized or vertical polarized. As I have told you before, S or vertical, these are interchangeable. And therefore, when you rotate your polarizer, this is in that path, it will be maximum when the transmission axis is also along. Okay? That clear? Yes.
So I said horizontal,
Uh-huh.
just because I didn't really know what the reference was. So I wasn't sure if it was referring to the surface.
Well, that's why I said refer to the drawing, the
Right.
figure.
But it wasn't necessarily. Like I wasn't sure which one was aligned with that direction.
Okay. Okay, that's fair. But I think we've been fairly consistent that vertical refers to vertical to the plane of incidence, basically. So the plane of incidence is taken to be horizontal, and then vertical is perpendicular to that. So that's what vertical usually means. That's the usual convention, and which is what we followed in all the notes and lab and so on. Okay, well, anyway, so maybe that was part of the confusion. All right, that's good. Hopefully we've cleared it up now, so you know for the future. Okay, so that's all. Those were the 2 questions which seem to give people trouble. So I'll go back to the slides. Why does it do that? I see. Okay, so before Thanksgiving, we covered the N coherent oscillator situation. I told you about how the irradiance pattern from that N coherent oscillators is a bunch of like principal maxima with like secondary, with like minima in between and secondary maxima in between. We discussed this in great detail, so I'm not going to go over it, but we derived the intensity distribution, which is this over here, sine squared N delta over 2 by sine squared delta over 2. We also did the line source in case we covered the line source as like a limiting case of this, where all the N coherent oscillators get scrunched up together, basically, but giving still a finite size. We also, in the supplementary video that I posted along with that lecture, I derived this more rigorously. So if you haven't yet viewed that lecture or seen that, you should go back and review it. Basically, I just showed there that, again, you get this function, which is sinc squared representing sine u over u, the whole square. So sinc function is sine x by x. So sinc squared is sine squared x by x squared. And in this case, beta is just representing that got left out, but it's basically representing the length of this slit times 2 pi over lambda sine theta. Basically, again, theta being the angle with respect to that source. And I showed in this video that a long line source looks basically like a point emitter at the center, emitting primarily circular waves in the XZ plane. That's because D, the length of the line source, is much greater than lambda. And as we have seen before, it's in that's when D is much greater than lambda, basically diffraction effects along that direction can be neglected. And we only need to worry about diffraction effects in the XZ plane, okay, which is where it looks like just a point emitter. So having done that approximation that the line source can be viewed as a point source, then we can think about a slit. A slit is like a bunch of line sources now arrayed along the along the Z direction. So along the Z direction, a slit is just basically a bunch of line sources. And each of those line sources then is represented by a little point source at the center. And then we have an array of these point sources again, arrayed along the along the Z direction, where the length of that array is this B over there, which is the dimension of the slit in that direction, which is summarized here. And so in the XZ plane, we have a coherent line source with length B. Again, we can use the beta equals KB over 2 sine theta. So now beta represents not this dimension, but this dimension, because that's the relevant dimension, because that's also the one that's comparable to lambda. Okay. So that's where the diffraction effects will be actually more appreciable. So again, we have the same function, the sinc function, sine beta over beta whole squared, but now beta represents KB over 2 sine theta. Okay, so the expected irradiance pattern looks almost like a little dot at the center, but with like additional dots representing the secondary maxima. And of course, in between, we have the minima, which we have shown. I explained in the last class how this can all be viewed as also a limiting case of the N oscillator situation, because I'm not going over that again, but that is basically what you can do. Okay, and we discussed this irradiance pattern, how it looks. Again, this is just review. The irradiance pattern has a minima when beta equals pi, right? That's very clear because beta equals pi, denominator is finite, but numerator goes to 0. So it's easy to find the minima of these points. And of course, then the maxima are roughly in between, again, halfway in between those two. So that's what we find, or that's what we can see graphically. So the first minima essentially determine the width of this angular width of the central maximum, which we can also convert into angles, as I've shown here, by setting this beta equals pi, immediately gives us sine theta is lambda over b. Okay, and so this relationship again is borne out, which I've talked to you before, and it's very important to sort of keep this at least this one thing in mind when it comes to diffraction or interference phenomena, that the angles in Fraunhofer diffraction, the angles of these minima or the central maxima are typically determined by some ratio between lambda, the wavelength, and the slit. So lambda over b is roughly the width of this central maxima, or 2 lambda over b is the width of this central maximum. So, and it's discovered by integrating or comparing the ratio of the intensities within this to the ratio of everything that's outside this. You can find that about 80% of the intensity is in the central maximum. Okay, then you can be a bit more rigorous. Of course, the minima are still at beta equals plus or minus pi, plus or minus 2 pi, but you can also find the maxima's location, the secondary maxima location, by simply equating di over d beta. Since you have the relationship for I, the intensity, you set di over d beta equal to 0, and that gives us this relationship over here, which then gives us tan beta equals beta. Okay, and you can solve for tan beta equals beta by plotting tan beta and then beta, the line equal to just that line in this function of beta versus beta, and then wherever these curves intersect is where you're going to get the maximum. And as you can see, they correspond to roughly 3 pi over 2, 5 pi over 2, but not quite. There's a small difference between that and the actual those peaks. Okay. So that is a review of single slit diffraction. Before we move on, I think it's also important to have a physical picture of single slit diffraction, which is beyond the sort of mathematical approach that we have taken. And it's helpful because it kind of clarifies some of the ways in which we can think about the diffraction for other situations. So if you use the Huygens for now principle, then you can break up the slit into like multiple little point sources or secondary sources. Of course, there's an infinite set of them, right? And what you can do is think about the secondary wavelets that are emitted by these sources. And then one of the ways we can picture what's going on is we can divide up the source, the slit. I'm just going to write here, it's easier than trying to write it here, is I'm going to divide up the slit into halves, for example. So this is one very simple way to think about the interference between the two halves of the slit. So for example, if I take a point here and a point here, okay, well, it's kind of, if these 2 points were to interfere destructively, then every point which is below this one will interfere destructively with the point here. The below that will interfere with the point here, and so on. So that means that and of course, for destructive interference, the phase difference or the path difference between those 2 points must be lambda over 2. Okay, and which means that that's of course for half the slit, right? So if the distance between this point over here and this point over here is obviously b over 2 sine theta. We know that, we have done this several times, that for some angle theta, when b over 2 sine theta equals lambda over 2, you'll get destructive interference between the top half of the slit and the bottom half of the slit. Does that make sense to everyone? Well, and then that means that the total phase difference between the top and the bottom is lambda. Because if b over 2 sine theta equals lambda over 2, which means b sine theta equals lambda, which means the interference, the path line difference between the top and the bottom is b sine theta. Okay. So that gives us the first condition for a destructive interference, which is b sine theta 1 equals lambda. Oh, and by the way, I should mention, at the very center of the slit, all the secondary wavelets are going to be in phase because they all have equal paths to that point in the center. Therefore, there's a bright fringe at the center. Okay.
So can we see this as just an overlap of the two, like the blade within the lab we did the diffraction by the blade, and then this is just like
the blade is slightly different. Yeah. The blade is a Fresnel diffraction.
Because it's very sharp at the edge, but here it's not sharp.
Yeah, I guess so. I'm not sure. I'm not really sure what you're asking.
Yeah. So this cannot be seen as.
I mean, it's like 2 halves of like a Fresnel diffraction. But we are in the Fraunhofer limit here.
Yeah, but for blades, so when it's sharp and then the pattern is very phenomenal.
Yeah. Okay. Maybe. I'm not exactly sure what you're asking. So okay. Yeah, so for every point in the top half, there's a point in the bottom half which cancels out, and that gives us the first minimum. As we go further, that's this graph, this figure over here. Now, let's say from the top of the slit to the bottom of the slit, that the phase difference is now 2 lambda. Okay, for 1 lambda, we got destructive interference. For 2 lambda, what will happen is now we can picture this slit divided up into 4s. To quarters. So now, I divide that, and then that. And so now the phase difference between this quarter, between that and that, now, every point in this here is out of phase by lambda over 2 with this one. So that cancels out destructive. Similarly, every point here is out of phase from this one by lambda over 2. Okay. So from here to here, I didn't divide it up exactly to quarters, but you see what I mean. So that gives us destructive interference when b sine theta 2 is 2 lambda again. So this is how we get destructive interference whenever b sine theta equals m lambda, you see. And that is where the minima are, which is the same that we found by just setting beta equals pi. So, or 2 pi, etc. That's the same relationship. So minima of this pattern can be found by setting b sine theta equals m lambda. This is the physical picture for that. So we'll go one step further. This is a physical picture where I just argue about how the different halves and quarters and so on are destructively interfering, but we can also see this by using the Huygens-Fresnel principle and dividing up this entire slit into like little emitters and looking at each of them as contributing a phasor to the final result, the final phasor of the total pattern that we are seeing. So to do that, what I am doing now, this figure here shows the interference or irradiation distribution. Okay, so this is right at theta equal to 0. Then some other theta2, not the same as the theta2 that I put on the previous slide. It's just some arbitrary theta2 in between the first, and then the theta3 is where the minimum occurs, the first minimum. Okay, and then we have theta4, theta5, etc., where other secondary maxima or secondary other minima occur. Okay, so now let's look at the picture where we have each of these emitters over here. Now 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 emitters. I've just chosen 9 as an arbitrary number because it's easy to draw some finite number of arrows. So each of them contributes a little phasor. Okay. When we are right at the center of the slit, where that is theta equal to 0, each of those phasors is exactly in phase with the next one, right? Because the path difference of all of these is basically 0. So each of these contributes a phasor which is exactly in phase with respect to the other one. So beta, which is remember beta is kind of like dividing up the slit into half. So it's like the phase difference from the top of the slit to the half point to the center point. And delta 1 represents twice that. Okay, it's just the way the notation in your textbook has been made that delta represents twice that. So it represents the phase difference from the top to the bottom of the slit. Okay, or it's 2 beta. Okay, so in this case, all the little phasors from those 9 points all add up in phase. The total length of this we call as the total electric field from the plane wave. So the plane wave that's coming in has a total intensity or total electric field, which is E naught of 0. Okay, so that's the total length of this vector, and also the resultant of adding all the phasors is equal to that E naught of 0. Okay, so then I move to a point theta2 over here, some other angle, where now the total, that is the phase difference between the bottom and the top is pi over 2. And that means, of course, the phase difference from the top of the slit to the bottom of the slit is pi. Which means now if I look at, let's say, the center point in the slit, that has some phasor, let's call it R, which is like a reference phasor. Anything above the slit or above that point, above the center point, like one of the points which is slightly above, will have a phasor that's tilted clockwise, and one phasor that's below or the point below will have a phasor that's tilted downward. Okay, because they're obviously one is going this way, the other is going the other way. So those two phasors will be out of phase by plus delta 1 and they are plus beta over n, and the other one will be out of phase by minus beta over n. Okay. So we can continue like this. And as I said, because the total phase difference from the top to the bottom is pi, you can see that the final phasor is out of phase from the bottom phasor. This is the top phasor, and the bottom phasor are out of phase by pi. So they're pointing in opposite direction. So now to find the resultant phasor, again, remember the total length of these must be E naught, but the sum, which is the sum of the phasors, points from here, the beginning phasor, to the end phasor, which is this one. So this is E naught of theta 2. Okay, this is 0.2. And I can also now take n going to infinity. You see, I make the number of such phasors infinite. So then instead of being like, 1, 2, 3, 4, 5, 6, or 7, which I chose here, I make n very large. This will become like a smooth curve going from here to here. The total length of this curve, which is called a vibration curve, is still going to be E naught, the original electric field, right? Because that's just the total electric field that's incident on the slit. So that total length has to be preserved over here, but the sum of the phasors goes from this beginning phasor to the end phasor over here. Okay. All right, so that is the sum of the phasor, and that gives us the electric field at this angle theta 2. And yeah, so I just said that over here. So now we can go to some other point between points 2 and 3. So I had point, so now I'm choosing some point in between 2 and in between, and this 3 point, remember 3 is where the minima is occurring. So let's say that's delta 1 equals 3 pi over 2 over here, which is where beta equals now 3 pi over 4, okay? So again, remember delta 1 is from the top to the bottom, beta is like half of that, okay? So that's kind of pointed out here again. Again, n is very large, and again, because the top to the bottom is now 3 pi over 2, you can again see that this is the beginning phasor, this is the end phasor. If I extend them, they intersect at a 90-degree or rather 270-degree angle over them. Okay, that's the angle between the beginning phasor and the end phasor, because that's the total path difference or phase difference between the top and the bottom of the slit. So that tells me what the beginning phasor should be and what the end phasor should be, and then I just connect a smooth curve between them. So that makes the drawing of this curves very sort of easy, basically. That's the vibration curve. Now I can go to the minimum. Now beta delta 1 equals 2 pi, beta equals pi. Now you see that from the top and the bottom, these two come full circle, because now that from the top to the bottom is like a 2 pi rotation of the phasors. So I come full circle and the vibration curve basically comes back, and the resultant phasor then is 0. And I can do this again at another secondary maximum. And now we can see we kind of can justify better why the secondary maximum is close to 3 pi over 2. Okay. This shows it as exactly 3 pi over 2, but you can see there's a small, it's not quite maximum, or not quite as high as it could be. That's mainly because what happens is that there's an effect that we have not taken into account, which is called the obliquity factor, which I'll introduce in the next lecture about Fresnel diffraction, which just says that as the angles are increasing, some of these phasors aren't quite equal to each other. There is some small difference in the angles. But okay, that's a secondary sort of approximation. Something to a first approximation, if you take them all equal, then this should be where the secondary maximum occurs. So here, beta equals 3 pi over 2, and therefore the phase difference from the top to the bottom is now 3 pi, which means, again, the first phasor and the second phasor are out of phase by pi, or in this case, 3 pi. Okay, and continuing on, we get a second minimum over there, and delta 1 equals 4 pi, beta equals 2 pi. And again, this vibration curve, as it's called, circles around twice, and comes back to the original starting point. So this is the physical picture, but now we can do the math. So we take the arc length, which is, as I already mentioned, E naught of 0 always is the arc length. So in this vibration curve, the arc length is 2 times r beta, right? Where beta is this angle between the top and the delta is the total angle between the first phasor and the second phasor. So that's this delta, which is divided up into 2 halves, beta, which is equal to beta, okay? And now in this triangle over here, I can now calculate that's just r sine beta, and this triangle is also r sine beta. So we see 2r sine beta, which is the length of this part, and that's the total phasor. That's the actual electric field from this addition of all the different phasors. And of course, to eliminate this r, I just use the fact that 2r times beta, which is the length of this curve. So this curve has a length 2r times beta, which must be equal to the initial electric field E naught of 0. So we get that E naught of theta divided by E naught of 0 eliminates this r, the radius of the circle, which is then sine beta over beta. Okay, so let's do a problem. So find the width in centimeters of the central maximum in the setup below. If the focal length of the lens is 100 centimeter, wavelength is 532 nanometers, and the slit width is 0.25 millimeters. Okay, I'll just do this problem really quick. It's fairly straightforward. It's just plugging in some numbers, but it's helpful again to always keep in mind the physics, which is that, as I mentioned several times, if you take that intensity distribution, which looks like this sinc square function, then the width of this irradiance distribution is delta theta, which is on the order of 2 lambda over b. Okay, just remember that we want the first minimum, and that is always going to be given by this lambda over b ratio, and then therefore, so this is lambda over b. Again, just remembering that physics, even without knowing the sort of the exact function, but of course, you can also solve from b sine theta equals lambda, and you'll get sine theta equals lambda over b, and therefore for small theta, theta is approximately lambda over b. So that gives you the same answer, but this is just from the physics of diffraction, or all of these interference phenomena are always going to be proportional to some lambda over the slit width. Okay, and so that's delta theta is lambda over b, and therefore we now have the width of the central maximum, and it asks us in the setup, it gives us that this is the slit, then there's a lens, okay, and the lens is placed a focal length away from the screen. Okay, this is the Fraunhofer setup. You should always know this, that this is how the Fraunhofer setup is going to be, because you put this lens and it's a focal length away, which means that effectively that this has been placed, the source or whatever has been placed at infinity, and so has the image. Okay, source we're assuming is planar waves, so that's already at infinity. And by putting this at a focal length away, we place the image also at infinity. Okay, and therefore the that basically only the plane waves coming from this system are going to get imaged to a point over here, which means that we can now calculate the distance to the first maximum, or sorry, first minimum, which is this delta theta. So in this figure, we can see this is f over here, and that is y. So we can say y equals f times tan theta. Okay, and therefore delta y is approximately f times delta theta. Okay, and therefore the width of the central maximum is basically delta y is equal to 2 lambda over b times f. Okay, is that clear to everyone? Why we are multiplying by f? Any questions? So placing the screen at a focal length away is effectively like placing the slits at infinity away from there. So that's like in the far field. Okay. All right. So that is the okay. I'll let you plug in. Well, maybe we can do it. Let's see. What is lambda? 532 nanometers. So I mean, usually the main thing that you have to be careful about is just keeping the units consistent. So 2 times 532 nanometers, I just write it as microns. And the slit width is 0.25 millimeters. So let's call that 250 microns times b times f, which is 100 centimeters. So microns is the same unit, so that's okay. Let's see. This is roughly approximately 2 times 10 to the minus 3, approximately, because 225, 500, okay. And then, of course, just taking into account that this is 0.53 divided by 250. So times 100 centimeters. Okay, so that's approximately, I think, 4 millimeters. Okay, if I made a mistake, you guys can figure that out, but it's just calculating that. Okay. the last point on this slit, single slit diffraction is that we've been illuminating with a single point source, of course, after using a lens to make that point source as just a planar wave. But we can also imagine a line source in the beginning, so like a filament lamp or something else. Well, a single point source should get imaged in our Fraunhofer setup to a single point source over here. So if you have an array of point sources, you'll get an array of points imaged over here. And then with each of those, there's an associated diffraction pattern, which is sort of pictorially represented here. So this is what we expect, that a line source in the y direction will get imaged to a pattern of dots in both the y and the z direction. Okay, the dots coming from diffraction in the in this z plane, xz plane, and then the length along the y direction just coming from the fact that you have a line source. And there's not much diffraction going on in the y direction because that we are presuming that the slit is very long in the y direction compared to wavelength. Okay, and then if you have a plane wave, well, now this is like a series of like it's essentially, of course, an infinite extent in the y direction, and it's also basically imaged to a plane wave in the z direction. So this will now get mapped to bands along the y direction, basically. Essentially, you can think of it as I'm just illuminating the entire slit with a uniform illumination. So I get uniform illumination along the y direction, but then you get the diffraction along the other direction, which is the z direction over here. That's to either side. That's the z direction in our notation that we had chosen when we did the problem. And then if you just sum up the intensity along the y direction, then you get this peak over here, and then the adjacent peaks with the minimum in between, and this will again follow your sinc square irradiance distribution. Okay, hopefully that's all fairly clear. So I'm going to stop talking about single slit, and I want to move on to double slit diffraction. Okay, so the first thing to sort of think about in this problem is that you have double slits. Okay, so of course, if the two slits were infinitely narrow, we would return to our Young's double slit problem. So meaning, if this B was just extremely tiny, almost like a point source, then that's just like our Young's double slit problem. Okay, where all that matters is the separation between the slits. And notice I chose the separation between the slits to be A, which is the same thing we did in Young's double slit. We assumed that the separation between the two sources was A. Okay. And so now again, so what we are expecting physically, hopefully is clear to you, is a superposition of both interference from Young's double slit and diffraction, which we just read about from the single slit. So that's what you should hopefully physically expect, and that's exactly what happens in the problem. Okay, I'll not go too much into the math of this because, as I said, the basic physics hopefully is clear, and from that we'll be able to derive the total irradiance distribution. Okay. So exactly as I just said, that the total field in this approximation is a sum over both slits. I'm not writing the explicit forms for these functions. That was done in the line source video that I did last class. So we're not going into those functions, but basically we have the answer from those line slits. And all we need to do, that is what I mean is, again, we break up each of this into a line source like this, which is just a single point source in this direction. And then we have done the integral along this direction to get the irradiance distribution from a set of sources in the z direction, which is then, that is just this minus b over 2 to b over 2, f of z dz. So we just worry about the extent along the z direction.
Sorry, so what the approximation is we expand the function to second order.
First order, I believe.
So the fourth order.
Yeah, first order.
The first order.
Yeah. And then for the second slit, all that changes is that the limits of the integral, instead of being from minus b over 2 to b over 2, the second slit is displaced by the amount a. So it's a to the minus b over 2 to a plus b over 2. That's again going back to this drawing. The origin is in the first slit, and then the second slit is then displaced by a. Okay. The origin is in the middle of the first slit. So it goes from minus b over 2 to b over. All right. So, okay. So those integrals were done before. So what we have to do is just look at the total answer, which comes out here. Again, I'm skipping those integrals because, as I mentioned, the physics of it is hopefully clear to you that it's going to be a superposition between interference and diffraction. Okay. Interference just represents finite number of sources in superposing, and diffraction represents sort of an infinite set of sources superposing. So the superposition of all the little sources inside each slit, that's the diffraction. And then the sum of the two slits, that's interference. Okay, that's just a silly way that we give names to essentially the same phenomenon, which is superposition of the electric fields. So exactly as we thought, there will be a component. This is just exactly the diffraction from a single slit multiplied by this term, which represents the electric field of two sources, basically. And the first is just a circular wave, basically. And the second is just the same circular wave, but with a phase difference over here. This phase difference depends on the separation between the slits. Okay. Okay, so that can be rewritten using the trigonometric identity. Sine A plus sine B is equal to 2 times cosine A minus B times sine A plus B. Okay, that's just trigonometric. So we get this relationship. And of course, this is the electric field, the irradiance. When you square this, you get sine squared omega t minus kr plus alpha. And then when I integrate that and take the time average, remember, because omega is very fast and we usually time average over some finite duration, which is much longer than an optical cycle, the time average of this whole thing is just going to be half. So this basically falls away. Okay, it becomes just a constant factor when you calculate irradiance. But it's helpful to kind of look at this expression and see that this term over here, so anyway, as I said, the first term is just this omega t minus kr is the contribution from one slit. Okay, and so that's just the distance r to the point P where we're doing the observation. The second part, this alpha, comes from the slit 2. And this has a distance, now basically r minus a sine theta. Again, going back to sort of our original sort of Young's double slit. When the distance is a, then if I'm looking at some angle theta, okay, then this extra distance over here is r plus a sine theta. So if r is this distance from the first slit, then to the second slit, the distance is slightly increased. The amount by which it's increased is this little patch over here. And that's just r plus a sine theta. I can't write stuff with my cursor here. So it's just r plus a sine theta. In this case, it became r minus a sine theta because we were just, instead of looking up here, the way the orientation of the figure was drawn was we were actually looking down. Okay, so up or down. That just changes the r plus a sine theta to r minus a sine theta. Anyway, so that is where this extra term came from. So it's just the interference, as I said, from the Young's double slit. And as I said, anyway, this term, when I take the sine square, square everything and take the time average, this all just becomes half. So we are left just with sine beta over beta whole square times cosine squared alpha. Okay. And so if I now write that out, so that's our irradiance for I naught. I naught is just representing the intensity from any one slit. And then it's sine squared beta over beta squared times cosine squared alpha. Again, as I mentioned already, the physics of this is fairly hopefully clear. It's a single slit diffraction multiplied by double slit interference. Okay, so we can take two limits. That's always helpful. So the first limit, again, as I said, we take the limit where the slits are infinitely narrow or very, very small, so that KB is much lesser than 1, which means sine beta over beta is approximately 1. So then we just simply get the 4 I naught cosine squared and then K over 2 sine theta. This is the Young's double slit interference pattern, as expected. Okay. Then we can take the other limit where the slits, instead of being separated by a finite distance A, that slit separation goes to 0. Okay, then you can immediately see cosine squared becomes 1. And therefore, we get 4 I naught sine squared beta over beta squared, which is a single slit diffraction. but with double the intensity, because now we had two slits and we have made them into one, so we have double the source strength from any one slit, so therefore we get 4 times that. Okay. So and if I were to look at this pattern, here is the pattern from a single slit of a certain width. Okay, that's this pattern on top. That's just the diffraction pattern, basically. Okay, the spacing here, this position of these minima is just given by the same single slit diffraction formula. And then as soon as I introduce the second slit, each of these bands, these bright bands from a single slit, gets these narrow fringes in between. Why are those fringe spacings narrower? Well, as you may remember, again, the spacing of fringes is controlled by lambda over some dimension, right? So lambda over b is the width of the slit. B is usually smaller because it's the width of the slit than a, which is the spacing between the slits. So because b is much lesser than a, the spacing of the fringe minima for diffraction is further out, while the spacing of the interference fringes, which is controlled by lambda over a, that is much finely spaced. So the narrow bright fringes or the narrow fringes inside the diffraction maximum, or in fact in any maximum, any diffraction maximum, those narrow fringes, their spacing is controlled by lambda over a, which is the spacing between the slits. While the spacing of these bright fringes, or between the fringe and the max and the minimum, that's controlled by lambda over b, which is the width of each. Okay. Okay, so that's actually what I'm just summarizing here on this pattern. So because a is greater than b, the fringes from the interference pattern of two slits are more closely spaced than single slit diffraction. And this can sometimes lead to what is called a missing order in the interference pattern. What do I mean by missing order? Well, if I didn't have the diffraction pattern, then this interference pattern would just basically stretch from one infinity to infinity in some theoretical limit. Okay. But whenever the angle sine theta matches a minimum of the diffraction pattern, then I'm going to miss one of the orders from the interference pattern. And that will happen whenever a and b are in an integer ratio, as you can imagine, because when sine theta equals lambda over a and also some say 3 lambda over b, for example, then you're going to get a missing order. And you can even count up how many fringes there are here to give you some idea of this ratio. So for example, if I want to count the number of fringes here, I have a half fringe here, then I have 1, 2, 3, 4, 5, and then another half. So I have 5 plus 1 half and 1 half, so 6 fringes in the central maximum. Okay, and that gave me that a equals this 3b. So it's kind of like almost double this ratio. Okay. Yeah, so that's just again summarizing what I just said here. Diffraction minima occur when beta, which then controls sine theta, right? Occur at these points, and then the interference minima occur, or interference maxima will occur. Interference maxima will occur when alpha equals plus or minus pi, 2 pi, etc. While the minima will occur when alpha equals plus or minus pi over 2, 3 pi over 2, etc., etc. So, okay, I'm almost out of time, but I just wanted to
The quiz.
yeah, the quiz. Okay. All right, let's do the quiz.